My name is Günther Blöschel. I'm the EGU president and chairing this presentation. We will have the medal lecture for the von Humboldt medal, and I'm pleased to welcome Pradeep Mujumdar, who is this year's von Humboldt medalist. Pradeep, please come forward and deliver your medal talk.
Thank you very much, Professor Blöschel, for this opportunity. It's indeed a great honor and privilege for me to deliver the Alexander von Humboldt Medal Lecture of 2014. And I would like to begin by thanking the EGU, Professor Blöschel, and Professor Hans Theibo, Vice President, Dr. Philippe Corchiel, Executive Secretary, Professor Alberto Montanari, Chairman of our committee, and members of the committee for considering me for this award. I would also like to thank the people who have nominated and supported the nomination. Dr. Wouter Beitar, who nominated, he is from Imperial College London, Professor Vinod Gaur of India, Bhanu Nipane from UNESCO Paris, Dragan Savage, University of Exeter, and my colleague, Professor Manohar. I suspect this honor is given for exceptional international standing, is what the letter says, for people working in developing countries. And I come from India, and I value my collaboration with a large number of colleagues, international colleagues, who have given me this exposure. And just a few names there. Professor Toshiharu Kojiri, late Professor Kojiri, who was in DPRI, that is Disaster Prevention Research Institute at Kyoto University, Japan. Manolal of Columbia University. In fact, Professor Kojiri invited me for the World Water Forum sometime in 2000 or 2001. And that is where this long journey has begun, of interfacing with the international experts and participating in a large number of international meetings and so on. And Professor Upmanulal has been a mentor and an inspiring person for me in terms of the advice and in terms of the student exchanges that we have had and so on. Then there is Slobodan Simonovic, University of Western Ontario, Ashish Sharma, University of New South Wales, Australia, Yengo Kim of Seoul National University, of course, Bhanu Nipane, UNESCO Paris. And this is a large and formidable consortium through which we are taking up a major project now, Wouter Beitar Imperial College, Annam Beach Imperial College, Andy Turner, University of Reading, Chris Jackson, British Geological Society, Andy Mackenzie, and Charlie Williams. And recently we have taken up a project on urban flooding, where we are looking at development of the convective systems in the urban flooding settings. And the forecasts of the convective systems are being provided by Dev Niyogi of Purdue University. This project has just taken off, and we are quite excited to work on this project together on Indian cities, the flooding of Indian cities. So the work that I'm going to present would be perhaps a mundane level work for those who have already worked on climate change impact issues, but I would emphasize more on the quantification of uncertainties when we come to hydrologic impact assessment using the GCM scenarios, the regular approach. The work that I'm going to present is thanks to these PhD students, the recent and current research students, Dr. Subimal Ghosh and Dr. Deepashri Raje. They are already faculty members at Indian Institutes of Technology. Dr. Sheikh Rehana, who completed just recently, and these are the current students. I think Dr. Subimal Ghosh was the first in our country to start working on the uncertainty aspects of climate change impacts. And then these are the 3 series of PhD theses that we have got in the same topic. and Arpita Mandal is just completing her PhD thesis on detection and attribution of climate change. This talk has to be taken in the context of water management in the developing countries. So the climate change impacts as they affect the water management in already stressed water systems in developing countries is the focus of this talk. So just as a setting, this is where we are located. This is a place, and there is a large peninsular region, and it has influences from large climatic variations. And therefore, when we look at the water management scenario, when you think of either India or China, the first stress always comes from the population growth. As the population is increasing, the all India water availability is decreasing, and it's already under water stress condition. More importantly, about 75 to 90% of the water comes from our monsoon rainfall, which occurs only during the first 4 months, June, July, August, September, of the monsoon period. And about 80% of this water is used for agriculture purposes, irrigated agriculture purpose. So when we are talking about water management, unless we touch the irrigation, unless we look at the water stresses that are already happening in the country, we won't be able to contribute substantially. So the climate change is superimposed on such a scenario where there are already water stresses existing, and the climate change will be an additional stress in this context. So the national water problem, this is typical of many developing countries, but we'll take India as a case. We have large number of river systems, large river systems, Ganga, Brahmaputra, and you have Narmada here, Mahanadi, then you have Krishna, Kaveri, Pennar, and so on. These are our major sources of water. And we would be interested in looking at how the water systems in these river basins respond to global climate events. So the stresses actually come from these issues here. For example, extremely low efficiency of water use, particularly in agriculture, irrigated agriculture. In many situations, it is of the order of about 40%, 50%, and so on. Then frequent floods and droughts, contaminated rivers and groundwater, both due to natural as well as anthropogenic causes. There are some pockets here which are arsenic and fluoride affected because of geogenic causes, not necessarily always by anthropogenic interventions. And then there are also issues related with over-exploitation of groundwater, mainly because of the electricity subsidy. In several places, the subsidies are, the farmers are not charged at all for electricity, and therefore there is no penalty for using groundwater. And then there is a rapid urbanization that is taking place with very little scope for water infrastructure expansion. Now, these are some of the stresses that are already occurring in the country, and then climate change will be an additional stress, and therefore it is important for us to look at what are the additional stresses that the climate change will bring in as much as the water resources of the country are concerned, and how do we adapt to these situations for the next 2 or 3 decades. Now, this is a classical diagram where we look at the 3 major symptoms of climate change, namely that the global average temperatures are increasing, are known to be increasing, the precipitation patterns are changing, and the sea levels are known to be rising. Now, these factors, these 3 symptoms, so to say, have direct implications on several hydrologic issues. For example, the temperatures directly may affect the evapotranspiration, the water quality, apart from impacting the precipitation patterns. The precipitation patterns, change in precipitation patterns will affect the water availability as well as the hydrologic extremes of floods and droughts. On the sea level rise, because we have a long coastline, as I showed here, apart from implications on coastal flooding, it has implications on salinity intrusion because there is excess pumping of groundwater that is already happening, and then you are increasing the gradients. And therefore, the salinity intrusion into the inlands will become an important issue. So all these major symptoms of climate change, we need to look at with respect to their effect on several aspects of water resources. And these are the issues that we would be interested in. For example, at the large scale, we will look at how do water fluxes vary on catchment scale. And on water demands, as I said, the irrigated water demands are important for us. So the evapotranspiration gets affected. We look at how the evapotranspiration is likely to be changing. Similarly, on water quality and extremes of floods and droughts. And another important feature that we may have to look at is the delays in the onset of monsoon because of global climate events, which will have implications on agriculture. And of course, the coastal flooding and salinity intrusion. When we need to look at this, those who have worked on climate change issues will know that we have to rely on the GCMs, general circulation models, or the global climate models. But the GCM's ability, as you move from left to right on that table there, GCM's ability reduces, whereas the importance on the water management issues keeps increasing as you go from left to right. For example, on the spatial scales, the GCMs operate really on large scales, whereas what we as hydrologists and water resource engineers need are really the local scales. But the most important point is the variables of interest. We would be interested in variables such as precipitation, stream flow, soil moisture, etc. But the GCMs are notorious in their inability to produce these variables. So we address this twin mismatch, namely one of spatial scale and one of variable mismatch through downscaling. And typically being hydrologists, we fall recourse to the statistical downscaling, not the dynamic downscaling. The statistical downscaling, we bring down from larger scales to smaller scales, in fact, to station scales. And also, we reproduce those variables which are not well simulated by the climate models. So we achieve two things through the downscaling. One is from larger scales, we bring it down to smaller scales. Another is we simulate those variables which are not well simulated by the climate models by developing relationships between those variables which are well simulated by the climate models and the variables of interest in hydrology. That's the whole principle of downscaling. And those who have worked will know the details about this. So the classical approach to estimate the hydrologic impacts or to project the hydrologic impacts at river basin scales has been that you start with GCM simulations, downscale it, and then use the extraneous inputs on topography, land use patterns, all the catchment characteristics that are necessary for the hydrologic models, run the hydrologic models, and then generate the associated hydrologic scenarios. This is a classical approach that almost everyone uses. However, the important point here is that when we use this, there are uncertainties associated with each of these steps. For example, when we start with climate change projections from GCMs, there are a handful of GCMs, maybe about 30 to 50 GCMs now from the CME5 simulations available. And then there are a handful of scenarios, RCP, there are 4 RCPs, representative concentration pathways. Which model you choose and which scenario you choose, that's an important point there. So the choice of the model and the scenario introduces an uncertainty. Then there is a downscaling, you bring it down to hydrologic scales. There is a downscaling uncertainty associated with it. Then there are also uncertainties associated with the hydrologic models themselves. And typically what we do is that the extraneous inputs that are putting into the hydrologic model in terms of the land use, in terms of the vegetation, in terms of the soil characteristics, etc., these are held fixed for the, typically they are held fixed for the projection period, let's say of 3 to 4 decades and so on. Now, all of these will introduce several levels of uncertainties. And when we do this future water resources scenarios at river basin scale, unless we quantify these projections or qualify these projections with the associated uncertainties, they will not be of much use for the policymakers. So the main research focus in our group has been on quantification of these uncertainties. As you can really appreciate, there are both aleatory as well as epistemic uncertainties associated with the climate change impacts. So the aleatory uncertainty is actually irreducible, the probabilistic type of uncertainty, whereas the epistemic uncertainty, which we generally address through fuzzy systems, the possibility theory, imprecise probabilities, and so on, that is reducible in the sense that as you impart more and more knowledge to the system, the uncertainty can be reduced. The climate change impact procedure, as we generally follow, is burdened with both types of uncertainties, and we need to segregate, we need to quantify both of these. And there are methodologies available which will address both these types. And these are the types of methodologies that I would be talking about. Imprecise probability, possibility theory. Then there is an evidence theory, DS theory, that is the Dempster-Schaeffer theory, which uses this information provided by the climate simulations as an evidence of one of the pathways. And then there are ways of combining the uncertainties. So as an example, we take the Orissa region in the country, which is on the eastern side. Typically what we do is that we superimpose the GCM grid points on this and then develop statistical relationships between the hydrologic variable of interest, precipitation in this case, and the variables that are suspected to be driving the precipitation. So they are called as the predictors. So we use the predictors and then develop statistical relationships between the hydrologic variables and the predictors, hold these statistical relationships sacrosanct into the future, use the corresponding GCM simulations on the predictors, and then get the associated hydrologic projections. Now, this is the general philosophy of statistical downscaling. When we do this, as I said right at the beginning, as you change the GCMs, as you change the scenarios, you get a different type series altogether. So you get an ensemble of projections into the future. And this is on SPI. That means we convert the monthly rainfall into the standardized precipitation index and use the drought indicator, the SPI as a drought indicator to simulate into the future. When we do this, we start, as you can see, you get a spread of the time series. And this spread we need to look at with an implication on the policy, and therefore we start addressing uncertainties associated with this and provide probability distributions in three different ways. One, because of our lack of knowledge or because of our ignorance, we assume first, at the first level, that all models, all scenarios are equally likely. Then we look at how the model scenario combination works in the recent past, assign weights to those. And then the third level is not only you look at the past, because in the past you would have done some bias correction and then brought them, all of them together. And then when you leave them free to work into the future, they start falling apart again. So we look also at the future, how well they are performing together, and then assign weights. So this is the first level of addressing uncertainty, simply assign weights and provide probability distributions associated with these simulations. Remember here the sample size that we have is quite small because you may be working with about 25 to 30 simulations, model scenario combinations, and this is shown for the third assessment report, quite an old work here. And therefore, we start looking at the non-parametric distributions. We provide the non-parametric probability distributions. The question that we address is how are the probability distributions of the drought indicator likely to evolve in future? And the same thing we do with the conditional random field related downscaling. The conditional random fields have the advantage that you are talking about the conditional probability P, y given x, where y is your hydrologic variable, x is a vector of all the predictors. And this has the advantage that you don't have to worry about the interdependence of the variables x. And we will be also able to tell through the CRF models the most likely CDFs, most likely out of a large number of simulations that you produce, you can pick up the most likely CDFs for this particular variable. And this, you use, once you come to the daily scales of rainfall, you use these to also look at the wet spells and the dry spells, how the probability distributions of wet spells and dry spells are likely to evolve in future. Now, as I mentioned, the first level is, because of our ignorance, we are talking about all the time series to be equally likely, and that is how we have formulated the probability distribution. Now, when we start looking into the future, some of the models, as you can see, will start falling apart. In the bias correction, we would have brought all of these together, and then as you leave them free, some of the models will start falling apart. So how well they are together, we address this question and assign weights depending on how well they are together in the ensemble. And we provide the weighted probability distributions associated with that. The way we assign weights is a very elegant procedure called as the reliability ensemble averaging, which looks at both the recent past as well as into the future, and then assign weights. And we provide weighted probability distributions, both looking at the past, recent past, as well as into the future, provide weighted probability distributions of the rainfall. However, what we did now is that all the information that is available from many of the models, many of the scenarios, we have just combined in some sense, some statistical sense, and then provided one probability distribution. And there is a caveat here, that reducing the past, the present knowledge about climate sensitivity to a single probability distribution would clearly misrepresent the scientific disagreement. One of the models may be right. It may be crying out loud that, look, this is different compared to everything else. But what we have done is we have combined everything and then provided one single probability distribution. To address this particular point, we use the imprecise probabilities. Remember, we are talking about small samples, small number of GCMs, small number of scenarios, and therefore we may have totally missed the picture of how the future is likely to evolve. And therefore, instead of providing single-valued probability distributions, we provide an envelope of probability distributions using the imprecise probability concept. The imprecise probability concept is quite simple, where you use the parameters. For example, if you are talking about the Gaussian distribution, you use the parameters mu and sigma as interval gray numbers, and then there are ways of estimating these distributions, and you get an envelope of probability distributions. Now, this will give an indication of what is the maximum probability that I can expect from this particular system for that region. What is the minimum probability? So the probability range is what we get. The bounds of probability is what we define through this particular exercise. Then we address the question, there are model scenario combinations, and which of these model scenario combinations will best work for the post-1991 conditions? Because typically we use 1961 to 1990 as the baseline period, and after the 90 period, we use it as the period where the climate forces are visible. Now, this we do through possibility theory. Possibility theory is slightly different from the probability theory in the sense that it assigns possibilities of which scenario, which model best represents the current conditions. So you look at the current conditions, you look at the model scenario combinations for between 1990 and let's say 2005. Remember, I am talking about the third assessment report, therefore the scenarios were available between 1990 and 2005. And those things we use and look at how well the past is able to, the recent past is able to be represented by this, and assign possibilities corresponding to that. Now, the possibilities are non-additive, unlike probabilities. So if you have total ignorance, that means, let's say that we are talking about all time series being equiprobable, then we assign a possibility of 1 to each of them. So the possibility will get adjusted according to how well the scenarios are able to represent the current picture. And the uncertainty associated with, let's say, the scenario is actually the difference between these two. This is GCM plus scenario, and then you also have associated with models, the uncertainty associated with this, and only the scenarios. So you can segregate the uncertainties associated with just the climate models, just the scenarios, and so on. And then we conclude that in fact, many other researchers have concluded earlier that the uncertainty associated with the models as far as the hydrologic impacts are concerned with this standard procedure of downscaling using the hydrologic models and so on, uncertainty associated with the GCMs is much higher than the uncertainty associated with scenarios. Perhaps this is counterintuitive to the atmospheric science people because they often advocate that the choice of the scenario is more important for impact assessment. The next point we address is that, as I said, the statistical relationships that we develop for the downscaling, they are held constant into the future. And therefore, the non-stationarity associated with the statistical downscaling is often not addressed. So what we now do is, from the smaller scale, although we are interested in smaller scale, but we also look at how the natural modes of frequencies are changing. Let's say you look at the geopotential height at certain level, 500 HPA or some such thing, and then relate your downscaling relationships with the way the frequencies of these natural modes are changing. We do the clustering on these large-scale natural modes and then develop these relationships associated with each of these clustering and look at how the relationships will change with respect to the clusters. So we develop, instead of developing one relationship, let's say we had 5 clusters, we develop five relationships, and then you look at how the climate simulation, in the simulations, how these clusters are changing. According to that, we use the relationship. The next part we would be addressing is that you get different climate simulations, different scenario simulations, and for different downscaling, you get a different simulation, and so on. We use all of these as evidence and then try to see whether we can combine this evidence in some sense. Because of our ignorance of how exactly the future is likely to evolve, we simply use this as evidence and combine the uncertainties associated with it. There is a concept of plausibility and belief in the Dempster-Schaeffer theory, and this will actually give, in some sense, the maximum probabilities that are possible. Using this, then, we combine scenario uncertainty. We also combine across the clusters, we combine the evidence. Across the models, we combine the evidence. And then provide, there are several ways of combining these evidences. As you can see, there is a Zhang's rule, there is a Dempster's rule, and so on. So using all of these, we combine these and then provide the evidence of what is likely to happen in terms of the extreme drought, severe drought, moderate drought, and so on. So essentially here, the idea is that you use all of this information provided by the climate model simulations as evidence and combine these evidences and then provide the possibility of the belief and plausibility distributions. Now, simple applications of all this. So what we have done so far is that we have been able to get the probability distributions. We have been able to combine the different simulations provided by GCM scenario combinations and provide probability distributions, possibility distributions, as well as the evidence in terms of the plausibility and belief. Now we start looking at some very straightforward applications. For example, we look at the stream flow and then ask the question which are important for hydrologic designs. How the flow duration curves are likely to change in terms of using different models, different scenarios, and so on. And again, you get a spread, and we do some kind of a combination of these and get to those particular flow duration curves. We also look at extreme scenarios of demands increasing. This is done on a very non-rigorous way, but we use it as really an extreme scenario of demands increasing. And we also look at the flood peaks that are likely to change. At the same time, the seasonal water level coming down. So the seasonal water may be, the quantum of seasonal water may be coming down, but the flood peaks may be increasing. All of this we'll take and then integrate into a stochastic optimization model and look at how the policy needs to be tweaked or how the policy can be analyzed into the future when such a scenario occurs. The seasonal water level may be coming down, the peak floods may be increasing, and the demands, irrigation demands may be increasing. Can we maintain the same level of performance in the future as we have it today? That's a question that we address through this. And provide, this is just done on academic work. It cannot be directly applied as of now. But the idea here is that we say how the flood operation during the floods needs to be tweaked in that Mahanadi River, keeping in place the same level or the best level of performance on the hydroelectric energy as well as on irrigation. Now this is what we do on that. Then we ask the question, which is rather challenging, which is also perhaps may look to be an absurd question to ask, because from the GCMs we are coming up to daily levels, but now we start looking at, can we relate this with what is happening on the urban flooding scales, which are typically of the order of, we would be interested in short duration, high intensity rainfalls of the order of 15 minutes, 30 minutes, and so on. As a first step, we simply look at the historical data. The historical data shows here, now this is a complete data that is between 1969 and 2003. If I simply split that into two series, I get the IDF relationship. This is for a return period of 10 years. It indicates that the intensities at a particular duration are in fact increasing. However, I must immediately qualify that we are using for splitting, it's only a 16-year data, and therefore this cannot be taken as a conclusive result. However, this is an indication that perhaps the intensities are increasing. Now this, we do it slightly more rigorously by using CMIP5 simulations. We use 85 simulations. We would have come up to daily scale. From the daily scale, we bring it down to sub-hourly scale by using stochastic disaggregation. In fact, we use a simple scaling law there. We are using the general extreme value distribution with mu, sigma, and xi as your parameters. And for the mu, sigma, and xi at the daily level and at, let's say, sub-hourly level or 6-hourly level, etc., we develop a scaling relationship. We have a simple scaling in this case, and then generate the IDF relationship associated with that. As we can see, as the duration increases, there is not much of a difference between the historical as well as the projected. But when the durations are smaller, let's say we are talking about 1 hour, half an hour, 15 minutes, etc., these are the types of times of concentrations that we get. And this is where the uncertainty increases, as well as it indicates that the intensities are likely to increase. So these are from 85 simulations from the CMIP5 models, and the worst scenario of 8.5, RCP 8.5 is what we use. And then we also address the uncertainties associated with the intensities that we get. This we do through the Bayesian method with the prior distribution, and then the likelihood function, you get the posterior distribution. And then you resample that using the MCMC, that is the Markov chain Monte Carlo, and then get a distribution for the intensities at various durations. Now this is, for example, you are talking about half an hour duration. Now this is the historical, and then with all these simulations, etc., we get such a band here. And this, in fact, is it represents a distribution. Now these distributions, as time progresses, as the duration increases, there is not too much of a difference between the observed as well as the projected. But the lower durations, typically of the order of half an hour, 45 minutes, 1 hour, and so on. Now there is a large uncertainty associated with this, and I must again qualify that using the GCMs at such low durations, although we would have come from the GCMs only up to the daily level, but from daily level we would have done some stochastic disaggregation and brought it down to half an hour scale and so on. Now this procedure itself needs to be tested more rigorously. And therefore we provide intensity for a particular return period as a probability distribution, both for historical as well as for the future, for different scenarios. So instead of giving single valued IDF relationship, we now provide distributions of the intensities corresponding to a given duration for a return period. Then the next question is obviously we look also at the water quality. Now, any of our standard procedure is that from the GCM simulations, you run a hydrologic model. So instead of the hydrologic model, we now run a water quality model. Water quality is quite sensitive to stream flow, changes in stream flow, changes in temperature, changes in relative humidity, and so on. So all of these, we bring it down on scales and run a water quality model and look at, again, the context of developing countries is important here. There are large number of effluents that enter, and also there is a non-point source pollution that takes place because of the runoff that joins through the agricultural fields, picking the pesticides, fertilizers, and so on, and that has implications on the pollution. Now, on the same datum status now, you start reducing the stream flow, you start increasing the temperature, then what happens to the first level of water quality indicator, namely the dissolved oxygen? Simply you run a Quail-2K model, some EPA related model, and just increase the temperature and reduce the stream flow and see how the dissolved oxygen is likely to respond. We have not touched the GCM set. So it obviously indicates that, and why do we reduce the stream flow? We look at the historical trends of the stream flow, and then there is a significant trend of stream flow that is reducing and the temperature being increasing, and using that we construct hypothetical scenarios and look at how the quality is likely to respond. And this we do much more rigorously using the statistical downscaling techniques. Look at which are these variables which affect the water temperature, which affect the water quality transport, and use these variables and downscale them, use them as predictors, so predictants. Use all of these, downscale them, address the uncertainties, and look at how the dissolved oxygen is likely to change. Of course, this may look to be alarmistic in the sense that we have done some exercise, some combination of some models, some GCMs we have taken, some downscaling we have taken, etc. But the way we communicate these results to the policymakers is important in the sense that these results are all burdened with uncertainty. So unless we address the uncertainties and communicate the uncertainties properly to the policymakers, this will be of not much of a use. The best part of D&A studies, or in fact in any climate studies, what we do is that we take a data set and then do several circuses on that. You transfer it onto, you take a principal components, take first 3 principal components, transfer that into another map, and so on. So we are really doing several things that are possible on the data, and then want it to say something that we want. And that's the message that says. So you torture the data enough, it will confess to anything. So much as a criminal leaves a fingerprint behind, if there is in fact a climate change signal on the hydrology that we are seeing, let's say we are looking at the stream flow at a location, if indeed there is a climate change signal, then it would have left a fingerprint on that. So our aim is to capture this fingerprint and see whether we can say that yes, we have seen a hydrologic change, but whether this change is in fact due to climate change or it is just because of the natural variability. And that is what is done in D&A analysis. That is a detection and attribution studies. Detection is simply detect that there has been a change. Attribution is attribute the cause why this change has occurred. And broadly, the way we do this is that you look at the patterns and see whether the patterns that are simulated by the anthropogenically forced climate models in fact match the historical pattern. Or you also have a natural variability, whether this pattern that you are seeing now is in fact because of natural variability alone. Now this is what we do, and we use the optimal fingerprinting technique and look at the signal to noise ratio. We also look at how the signal to noise ratios are likely to evolve into the future. Remember here in this study we are only looking at the historical data, not anything to do with climate data and so on. So in this particular case, essentially we look at the solar volcanic runs, as well as solar runs, volcanic runs, and the anthropogenically forced runs of several models, and look at the patterns and try to match the patterns with the observed data, and see if we can conclude whether the change is in fact because of the climate change, anthropogenically forced climate change. In the Mahanadi case, I would quickly conclude. In the Mahanadi case, we could not unequivocally say that the change we are seeing is because of climate change, because there are several models that will disagree with this particular statement, and there are also signals from the solar runs as well as the volcanic runs that will not agree with the statement that we made. So in conclusion then, the science issues that we need to address vis-a-vis the climate change impacts are with respect to D&A studies at regional scales. We need to also now look at how the land use change is contributing to the change that we are seeing on the hydrology, especially in the context of rapidly developing countries like India. And we have taken now the large Ganga basin and seeing how the land use change that has happened because of extensive irrigation over the last about 3 to 4 decades, whether there is a feedback on large scales, the soil moisture regimes have changed, whether there is a climatic feedback from the land use change as well as the irrigation that happens into the climatic system. And that is what we do. And these are the science issues that we need to address. Can we look at the non-stationarities introduced by both climate change as well as anthropogenic change and the land use changes that are happening, and quantify and try to reduce the uncertainties associated with the projections? Because as I said, it is true that most of the change, most of the stress is occurring because of a large number of other related issues that I showed right at the beginning, water resource issues. But the climate change can be an added stress. So we need to segregate and address the issues related with climate change by itself. So in summary then, I think it is the responsibility of the scientific community to address, to quantify the uncertainty and communicate these uncertainties in a right way for the policymakers so that responses can be developed on local scales. Thank you very much for your attention.